And it gives me a great pleasure to introduce Stephen Schacht. I have known him since 1985, I believe. And this conference is a result of a meeting we had last June at Vanderbilt. And, well, you know the topic is going to be how maintainable is Linux. And Professor Schacht has been at Vanderbilt since 1983. He's an associate professor of computer science. And you know the topic, and here he is. Thank you.
Thank you. Thank you very much, Juan. And it's a real pleasure to be here. Good morning to you, ladies and gentlemen. The subject is Linux maintainable? The answer is no, and we can all go home now. Here are the list of my co-authors. The first 13 are Vanderbilt graduate students. Jeff Offit is the co-PI on the NSF grant that sponsored part of this, and Jill Heller is our statistician. In case you're wondering why so many graduate students are involved, work of this kind, everything has to be done independently by at least 2 different people, and the results reconciled. Otherwise, it's not going to be accepted by the community. Here is the overview of my talk. I'm first going to discuss a longitudinal study of 365 different versions of Linux. That's close to 1 billion lines of code, hence the large numbers of graduate students. I'm going to talk about definition use analysis. Then I'm going to compare Linux to FreeBSD, NetBSD, and OpenBSD. I'm going to be talking about a specific global variable called current, and I'll then come to conclusions and future work. And the acknowledgement this work was sponsored in part by the National Science Foundation. The first topic I want to discuss is a longitudinal study of 365 versions of Linux. First, the background information. Coupling is, as I'm sure everyone knows, the degree of interaction between any 2 modules. And if 2 modules share a common or global variable, we call that common coupling. The name common, for people who are 20 years younger than me, comes from Fortran, where the global variables were called common. So, for example, we might have module A and module B, both of which access the same global variable, call it GV. If module A changes the value of GV, then that may well affect module B. And this has got major implications for maintenance. That is to say, changing one module, module A, can change module B. And this is why common coupling is so dangerous. Continuing the background, unfortunately, we do not yet have a definition of maintainability. Since we don't have a definition of maintainability, there can be no metrics for maintainability. If you don't know what it is, you can't measure it. And therefore, the fact that common coupling has not been explicitly linked to maintainability, that's not surprising. What empirical evidence do we have? Well, we know that the stronger the coupling between modules, the more faults they're going to be. Because the more dependencies, you're going to get regression faults. Now, if you've got a lot of coupling, you're going to have a lot of faults. You've got to fix those faults. If a module is fault-prone, because of this high degree of coupling, it's going to undergo lots and lots of maintenance. And the more maintenance you do, we know compromises maintainability. So I believe that it is easy to believe that strong coupling can have a deleterious effect on maintainability. I think I want to just add something else that arose as a result of discussions yesterday after I prepared this talk. We cannot measure maintainability. We can measure maintenance effort. That is a well-defined quantity. We can say the effort is an average of 5 hours to fix each fault. Or the maintenance effort is $108 per function point for new code, whatever it is. So maintenance effort can be measured in terms of time and money. However, I'm dealing with open source software. With open source software, neither time nor money is recorded, and they will tell you neither time nor money is relevant. So that is the reason why I'm using an indirect method of common coupling. Right, the next background information I want to give before I can get to the Linux itself, I want to talk about kernel-based software. Many software products consist of two parts: kernel modules, which are present in all implementations, and non-kernel modules, which are chosen for a specific implementation. All the way, I'll be using this light blue for kernel for both words and diagrams, and I'll use this ochre for non-kernel. Example of software product line. You've always got the core, that's the kernel, plus the optional stuff. And similarly with an operating system such as Linux, you've got your kernel present in all implementations of Linux, plus non-kernel ones for specific architectures, for specific hardware, and so on and so forth. And the way I draw it, I always put a box around the kernel, reminding us that that's the central part, and then we've got the non-kernel modules outside. Now, a word of warning. The word kernel, unfortunately, is overloaded. If you're an operating systems person, then it's the part of the operating system that can execute certain commands. But in this case, it's a software engineering context. It's those modules that are present in all implementations of the software. So in the case of Linux, there's certain modules which every implementation has. That's it. OK. Now we come to the first of the four projects I want to talk about, a longitudinal study of Linux. Here's the reference. And I believe if you click on the link, you can download the paper. Work was published in February 2002. We examined 365 versions of Linux. There's nothing mystical about the number 365. That was the number that were available at that time. About 3 million lines of code each. So this was not exactly something I did over a weekend. Oh, the light is working. We looked for global variables. And then once we'd identified the global variables, we counted the instances of common coupling, either within the kernel, between two kernel modules, or between a kernel module and a non-kernel module. And this is the kind of result that came up. Let me illustrate what's going on. Think these lines each represent a different module. So there are 4 different modules in Linux shown here. If you want to know which ones they are, you'll have to look at the paper. So this particular module was present from the very beginning. And in the very first version of Linux, there were, about 150 instances of common coupling between this module and the rest of Linux. And it increased. By 365, it had gone up to about 1,500 instances. The heavy line is what we measured. The thin line is an exponential fit. And this is an unbelievably good fit to each of the curves. In fact, it's like a 99.4% fit. I don't remember the exact number, but you can get that in the paper. But you can see how close it is. In other words, what we found was that the number of instances of common coupling grows exponentially with version number. But the number of lines of code grows linearly with version number. And the conclusion is short and sweet. As Linux grows in size, it simply will be unmaintainable. Because exponential growth can never compete with linear. Question?
So how do we define an instance of common coupling? If one global variable is referred at 2 or more places, is that one instance? Or if it's referred...
If it occurs in... let me start that again. It depends on the specific context we're talking about. But in this one, we're measuring the coupling between this module and that module. I'm just trying to remember because I want to be very precise here. In some cases, we just looked, multiple instances were treated as one. We have figures for that. And in other cases, we took the number of instances, have figures for that. I do not recall whether that graph is the one or the other, but we've considered both of them. And you get the same answer. It's going up exponentially. Yes?
What exactly is a module in this context?
Sorry, a module is a Linux file is a module.
Okay.
Okay. I'm sorry, I should have mentioned that. Please, clearly there have been some things I've left out in my presentation. Please, question, yes?
So all the versions you're looking at are ordered by date.
Ordered by date.
It's not that you're looking at this version of Linux versus this independent version of Linux versus this semi-independent version.
No, they're ordered. We know I numbered them 1 through 365, and we've got. If you want to know what version 282 is, well, that may be the one issued on June the 13th, 1997.
And so you're looking presumably mostly at what Linux calls the kernel.
Look, yes.
Okay, fine.
Okay.
So is there any outlier that you throw out from the curve, or they represent the truth, all the data?
That's all the data. Nothing is, no outliers have been removed. I can say categorically. Now, these results, when I presented them, were, I say, widely and wildly attacked. Let me explain what happened. It was at the ICSI in Florida, the one that was cancelled from, or moved from Buenos Aires because of the riots. I think 2003? No, 2002. At a workshop, I presented this material. I've never before or since witnessed a riot at a scientific conference. I think that's the only term I can use. There were people jumping up and screaming, Linux is maintainable, Linux is maintainable, I don't care what you say. You shouldn't laugh, this is very sad. The problem is that for many people, open source software is a belief system. And when you attack someone's religion, they're going to turn nasty. And
amen, brother.
And this was touche. And this is what happened. Anyhow, I reported this to my co-PI, Jeff Offutt, who somewhat poo-pooed it. After all, my mother always says about me, I only opened my mouth to change feet. So so Jeff assumed that I'd made some similar stupid remark which had inflamed people. And in November of that year, he presented some of the same material at a panel discussion at a conference in Washington, D.C., and much to his surprise, he got much the same kind of reaction. However, unlike my reaction, which was negative, destructive, let's leave it at that. Denial, yes. He got two useful responses, not during the discussion, but afterwards. Two people came up, and one said, you know, you're being unreasonable. All operating systems have to use common coupling. So before you start saying that Linux has got too much common coupling, why don't you compare Linux common coupling with that in other operating systems? A very reasonable response, and I'm going to take that up in that section of the talk. Then another person came up and said, you're looking at the wrong thing. You shouldn't be looking at common coupling. You should be looking at depth use analysis. We took that seriously, and that's going to be the second thing I want to look at. Background for the second section of my talk. Every instance of a variable can only be a definition or a use. I'm not talking about a declaration, you know, defining that y is an integer. A definition means a setting of a value to that variable. So you can either change the value of y to 3 or change it by reading it, or you can use it if it's greater than 8 return, or set z to the value of y minus 2. But those are your only possibilities. You can either use the existing value or set the value to something. There's nothing else. The one's called a definition, def for short, and the other's a use. Now, the reason this is important is in maintenance, because a definition can affect a subsequent use, but changing a use can't affect anything. Because a use, you're just utilizing the value. So instead of utilizing the value 4, you utilize the value 5, so what? It doesn't affect anything else in the program. But if you change the definition, then all subsequent uses that depend on that definition are going to be clobbered. So therefore, from a maintenance viewpoint, what is important is not so much global variables themselves, but the defs, the definitions of global variables. So, okay. This paper has just been published in IEEE Transactions on Software Engineering. It's called A Categorization of Common Coupling and its Application to the Maintainability of the Linux Kernel. Again, you can download it by clicking on the link. The experiment was very simple. We just counted the number of definitions and uses of the global variables. We already knew what the global variables were. We knew how to count them. All we had to do is to take each instance and define it as a definition or a use. In more detail, what we did was we looked at a common coupling, and we discovered that there are many different types of common coupling in kernel-based software. And we categorized them in increasing order of the impact that it was going to have on a modification of the kernel. Let me explain. Here's a global variable, let's call it GV1. It's a category 1 global variable. Remember, it's in blue because we're talking about the kernel. It's defined in one or more kernel modules. It's not used in any kernel module. So if I mess up with this global variable, it can't affect the kernel. It can affect the non-kernel, I'm not worried about the non-kernel. Because remember, in something like Linux, the kernel is under very tight control. Anyone can write a non-kernel module. You want a driver for a laser pointer? Fine, you can write it and add it in. No one's going to say anything. But you try messing with the Linux kernel and see what happens to you. The kernel is the part that has to stay intact, secure, and not messed around with. So if you define something here and use it there and mess up your definition, changing a definition cannot affect the kernel, so I'm not worried about it. Category 2, it's defined in exactly one kernel module and used in one or more kernel modules. So module A is the tricky one. That's where it's defined. It may be defined 3 times or 7 times there, but it's only defined within module A. And if I mess up one of those definitions, I can certainly start messing up the kernel. So this is already starting to get dangerous, but there's only one place, one module, one Unix file, where problems can arise. It gets a little bit worse with category 3, where it's defined in more than one kernel module. So it's defined in A1, it's defined in A2, and used in one or more kernel modules. Now there's more than one place where if I mess up the definition, it can affect a use inside the kernel. Category 4 is bad. Category 4, it's defined in the non-kernel and used in one or more kernel modules. This is exactly the same as category 1, but with the arrow in the wrong direction. And this is the case where the inmates are in charge of the asylum. Because if a non-kernel module, which is not under control, can affect a kernel module, real problems can arise. So you certainly do not want to have, if you can possibly avoid it, category 4 global variables, because there, someone outside your control can play around with a non-kernel module and clobber your kernel module. But if you think that's bad, come to category 5. Category 5, it's defined here and defined and used here. So you can mess up here and mess up there, and in both places have problems in your kernel. A global variable defined in one or more non-kernel modules and defined and used in one or more kernel modules. The arrow goes both ways because it's defined in both places. This particular one is defined once, not used at all. In the non-kernel modules, defined twice and used 3 times in the kernel modules. So you can imagine that the worst thing you could possibly want in your operating system is a category 5 global variable, because they are big trouble when it comes to maintenance. And of course, you would expect that there wouldn't be many of these. Well, this picture, a little hard to understand, describes a variable called current, a global variable which is category 5. On the left-hand side of the screen it's in blue, it's in a box, it must be the kernel. On the right-hand side is the non-kernel, it's in ochre. Now, there are 12 kernel modules which both define and use current. So, for example, what's closest to me here? itimer.c defines it 7 times and uses it 9 times. These 6 modules here use current, but they don't define it. So it is defined in 12 kernel modules, used in 18 kernel modules, defined in 1,077 non-kernel modules consisting of 1,508 definitions and 7,290 uses. Now, this is bad.
So what is current other than that?
Current, okay. Can I respectfully, it's going to be my last topic, if I haven't covered it to your total satisfaction, get back to me then. Okay. It basically points to the current process. Okay, yes.
One more question. When you're counting variables,
yes,
it could be that you have a variable which points off to some large, complex, mutable data structure,
yes,
which has a number of positions in it, which are also mutable. Those other things do not count as variables.
No. In this study, I'll be coming to this at the end, we're doing what I call a large grain or large-scale study where the fields of current are ignored. We just take current, although it points to things which point to things which point to things. We just say if it's on the left-hand side, it's a definition. If it's on the right-hand side of the use, don't bother me. We've just completed a study, a fine-grained study of current, where we look at each of those individual fields and treat each of those individual fields separately as a separate variable.
And then next you can go recursive.
Absolutely, and we've taken that. That piece of work, the first draft of the paper I brought with me today for proof, on the trip for proofreading, it's not yet ready for. Yeah. Please.
In your historical context,
yes,
as it goes through, were you able to document how many times a definition was changed while maintaining the same verbiage, but was changed within?
We could have done. The only one that we evaluated historically is current. And I'm coming to the historical view of current. Again, if you're not happy, please. Good, thank you. Now, here are the results for Linux. And they are very worrying, in my opinion. These are the global variables in Linux. There are 99 of them. Category 1, I've got no complaints with. Category 2, okay. Category 3, I'm not too happy with. And there's quite a few Category 4 and Category 5, which I don't like at all. Inside the kernels, here's the number of definitions and the number of uses. And in the non-kernel modules, for Category 5, we've got 1,732 definitions. And that, ladies and gentlemen, is a matter of concern. Because it means there are 1,732 places in Linux, in non-kernel modules, where if you mess up a definition, you could mess up a use within the system. There's just too much level 5 common coupling. Most but not all of this is due to current. Total number of uses is also in the 7,000s. So, the conclusion for the second time is that Linux will simply become unmaintainable. Because with these huge numbers of definitions in non-kernel modules, see it's non-kernel, and I just did it in orange just to rub the point in. With these large number of definitions, there are going to be problems with uses inside the kernel. So, again, I believe Linux will become unmaintainable. Now, I want to compare Linux to the... Please, yes.
You have the numbers if you exclude current?
Yes, they're in the paper.
Okay.
The IEEE paper has them. Yes.
Can you give some examples of the non-kernel modules that are defining and using the current?
Just about everything. Current points to the current process, and also points to the stack. So just about anything that's going to be involved there.
Right. What kind of non-kernel modules are actually defined?
Drivers will do it. In fact, we've written another paper where we've looked at current in great detail. And I think something like 60 to 70% of them are in Arch, architecture modules, and driver modules. Okay, yes?
There might be something that has exactly one definition inside the kernel, but there's a function call that sets it that could be called from many other places. You're not counting those, right?
No. In the paper where we're going to look at aliasing, which I'll come to next, where we do look at that, but not in this paper.
So in some sense, you're really undercounting.
Absolutely undercounting. The numbers I give here, that 12,000, we've already found another 2,000 instances from aliasing. So, yeah, the number's going up and up and up. I will stick with this figure as a lower bound. Now, this is publicly available. Download Linux, do your own counting. I feel you will not get below that figure, but I've now got evidence that it's higher. Yeah. Okay, so now I want to compare Linux with FreeBSD, NetBSD, and OpenBSD, because I think the criticism at the Washington conference that all operating systems have to use common coupling is a perfectly valid one, and therefore our attempt to criticize Linux on the grounds of large amount of common coupling is unreasonable. So all I had to do is compare Linux with other open source operating systems. Here are the papers. There's two that have been submitted. One, maintainability of the kernels of open source operating systems, a comparison of Linux to FreeBSD, NetBSD, and OpenBSD. That's what was submitted. And then reuse efforts in kernel-based software. Oh, you can look at that, the data there. But here I've summarized it in one slide. And I think you'll find it pretty damning. OpenBSD, FreeBSD, NetBSD, and Linux. The number of global variables, roughly the same. Linux has more than the others, but, you know, Linux has more. Let's not be picky. The number of instances of global variables in kernel modules. Linux has got 3 times as many. Despite the fact that the size of the kernel is about 1/4 of the size of the OpenBSD kernel, what, 1/8 or so of the FreeBSD, and what's this, 4 or 5 times smaller than NetBSD. Please.
But if you say that many of these instances come from drivers, doesn't that mean that Linux maybe has more drivers and more support?
Yes, it's a much bigger operating system. But I'm just looking at the kernel now, and there are no drivers in the kernel. I don't know of any. So if we just look at the Linux kernel, the kernel is much smaller, but has many, many more instances of global variables. So there's too many global variables. Remember, this part of the talk is question. Surely all operating systems need global variables. Answer, yes, but Linux got too many of them. So just looking in the kernel, we've got a relatively small kernel and far too many instances. If you divide the number of instances of global variables by the size of the kernel, you'll see that the figure for Linux is like 10 or 20 more variables. Now if we go to non-kernel modules, where the drivers, architecture stuff, and everything, yes, it is a much bigger system. Linux is 3.3 million lines of code, the last version we looked at for this paper, and OpenBSD is only 1.4 million. But the number of instances of global variables in non-kernel modules is far, far higher. So this is about, what you say, 2.5 times as big as that, but 2.5 times this is 1,250, not 14,688. So proportionately speaking, Linux has got too much. And it is possible to write a Unix-like operating system, OpenBSD, FreeBSD, NetBSD as instances, with global variables. Of course, you've got to have global variables, but not too many excess of global variables, as in the case of Linux. And therefore, let me go. I shouldn't have said therefore. I forgot about this slide. I want to come up with the point of an unsafe definition. An unsafe definition is a definition of a global variable that can affect a kernel module if that definition is changed. So, for example, if you've got a definition that is in a non-kernel module that can affect a kernel module, that's clearly unsafe, because you don't want anything happening outside the kernel affecting the kernel. Even a definition in the kernel that can affect the kernel is unsafe. So we distinguish a safe definition, which can't affect the kernel, and an unsafe definition, which can affect the kernel. Unsafe meaning you're going to have problems with my operating system. And here is a diagram which shows the number of unsafe definitions in kernel modules per 1,000 lines of code. In Linux, there are nearly 17 unsafe definitions per 1,000 lines of code. In the others, it's of the order of 1. You've got like a 70 to 1, or here it's about 10 to 1 ratio. Unsafe definitions in kernel modules. Please.
What was the last kernel version you studied?
I think 2.4.20, I think. Okay. Again, the paper will have. I always hesitate to answer questions like that, because some graduate student normally goes back to the paper and adds an extra data point, and then I'm in trouble. So that's what I suspect. But just download the paper. You'll get, for each of these, we'll tell you the exact version we consider. Okay. Yes, please.
What caused Linux to be so different from others?
Well, I certainly don't want to have a libel suit on my hand. Let me simply say that the way that Linux was, in my personal opinion, the way that Linux was originally designed is the cause of this. Because when we look at current, we'll see that this problem was there from the beginning. If you look at even our first longitudinal study, I mean, I don't want to flip back to a very early slide, because I think people's eyes, when you go back over 25 slides, it's not a good thing to do. But if you just look at remember those slides showing the increase in common coupling, it started at the very beginning. So basically, if you start off with common coupling at the beginning, too much, you're going to get even more later on. Common coupling grows exponentially. We published a paper on something called clandestine common coupling, which basically shows that if you've got common coupling, someone else can add another module on, and that will cause more common coupling without you even knowing about it. So once the common coupling is there, it grows insidiously. So the short answer to your question is, it was there from the beginning.
So if I say,
let me act as a devil's advocate.
Sure.
If Linux is at a stage to get stabilized, right? So the exponential growth of this common coupling will stop or will gradually slow down and make it as best as like a linear growth with regarding to the growth of the code lines. That's not happening.
No. The only way that could happen is if, and I would certainly advocate this, if the growth of Linux suddenly stopped and Linux were essentially restructured. So if Linux was rewritten with the same identical functionality, but many, many fewer global variables, perhaps copying the BSDs or some of the other operating systems that we've looked at, then certainly the problem, the exponential growth might continue, but it continue a lot more slowly.
But that's not going to happen because these guys still don't think they have a problem.
Fine. I'm not going to argue with you with that point. But I'm simply... Yeah, we agree. Okay, so here are the basic results on the BSD papers. Linux compares unfavorably to the 3 BSDs with respect to every measure we considered, and I think there are about 15 in the paper. Total number of global variables, total number of instances of global variables in the kernel, total number of instances of global variable overall, number of instances of global variable per 1,000 lines of code in the kernel and overall, and I think I've got a few more here. Number of unsafe definitions of global variables in the kernel, number of unsafe definitions overall, number of unsafe definitions per KLOC, and so on and so forth. You can take any measure. Well, I don't know you can take any measure. Let me rephrase that. We tried to find a measure in which Linux would not be considerably worse than the others. We couldn't find it. There was a question somewhere. Yes, please.
So maybe I'm jumping a bit ahead, but your finding would suggest that the Linux release cycle would show signs of slowdown. Did you try to find a correlation?
Yes, we haven't found that. We're not at that point yet. I mean, Linux is still going fine, but the growth at some point, there has to be a problem unless Linux fixes it up. We know that there have been restructurings of Linux, 3 of them so far, but they're all very minor, involving essentially 3 different files. So this major restructuring hasn't yet been attempted, but at this point, we think Linux is okay. It's the future we're concerned about. Interesting thing we looked at least we found interesting, were the consequences for reuse. Because if you look, for example, at Darwin, Darwin is a reuse of FreeBSD together with Mach 3.0. So we looked at various operating systems and said, how easy is it to reuse them in some other product? And what we did is we took the operating systems, we said how many kernel components there were, we took the size of the kernel and the number of unsafe definitions per kernel KLOC, because these are the ones that have to be changed if you're going to reuse. You can see it's huge for Linux compared to the others. And the consequences are as follows. If you want to reuse 1,000 lines of FreeBSD kernel code, we have to modify 1.37 definitions of global variables somewhere else in the program, on average. If you want to reuse 1,000 lines of Linux kernel code, you've got to modify 134.08 definitions. That gives you an idea of the tightness of the coupling, the degree to which pieces of Linux depend on one another, assuming you want to reuse Linux somewhere else. FreeBSD has been successfully reused in Darwin. I don't know if Linux has been successfully reused. I've never heard of anything, and I think it would be very hard to do.
Can you just define reuse for me a little more clearly?
Yes. If I want to write an operating system, and I don't want to start things from scratch, I want to take an existing operating system, copy it into my workspace, make minimal changes to it, and utilize that instead of reinventing the wheel. And if I can do that with minimal effort, I've done a successful reuse.
Okay, and this paper is still being published, right?
This is still in the, yes, it hasn't, it's under review, yeah. There's 2 of them there, okay. Conclusion that we come to here is that operating systems do need global variables. There doesn't seem to be a way of avoiding it, but Linux overuses them. This has affected maintenance and affected reuse. Third, yeah, please.
So you compared kind of endpoints on that one. Did you chart the growth of the BSD ones?
No, we haven't had a chart.
Linear exponential?
No, we have not looked at that. The last topic I want to talk about is this variable current. And this, too, has not yet been accepted for publication. This one is still under review. So, current was first introduced in version 1.0.0. So it's been there for a long time. That's another answer to your question. Why are there problems? Because they were there from the start. In version 1.0.9, it was defined as a pointer to a task struct in sched.c. So current is a pointer to a task struct. Basically, current points to the current process. From version 1.3.31 onwards, it was redefined as a preprocessor macro. For example, version 2.4.20, which I think is the latest one for this paper too, current is defined as this macro, get current, an inline function that returns a pointer. Now, what is the difference between a macro and just a pointer? Effectively none. The functionality is identical. Efficiency is being improved here. The two implementations are exactly the same. So even though you will say, but wait a minute, current isn't a variable. It's a macro which returns a pointer rather than a pointer itself, that you're just splitting hairs. Basically, it's a global variable which is implemented as a macro which returns that global variable rather than the global variable itself. Okay. Data structure task struct describes some kind of process or task in the system. It has 83 field variables. This is in answer to your question. 60 are primitive, 3 are composite, and 20 are pointers to others. So you've got this recursion that you spoke about. So for example, in our definition use analysis, what we say is current arrow state is task running. Here's an assignment. Current's on the left. It's a definition of current. Or if we say if current arrow need to reschedule is true, set x to 1, otherwise set x to 0. There's no assignment here, we're just using it. That's a use. I don't care about the fields. I'm treating current simply as one global variable. And here are the number of instances of current that are going. As the size of the product Linux grows, the total number of instances goes up like this. It's getting big. In version 1.2.0, there were only 6 kernel modules which defined and used current, and 4 which used it, and only 129 kernel modules had definitions or uses of current. But as we go up to version 2.2.10, we've suddenly got, in this circle, we've now got 8, still 4 here, 508 non-kernel modules, involving 1,034 definitions and 3,277 uses. This figure you've seen before. This is the latest one we've evaluated. And as you can see, it's just getting worse and worse and worse. So, successive versions of Linux have got more instances of current. Successive versions of Linux have got a more complex type of definition-use relations that involve current. Please.
So for a long time since I looked at Unix source, but I remember there was this U variable that sounds very similar to this current variable.
Mm-hmm.
Did the NetBSD or the BSD versions you were looking at have this U variable?
You've got to have a pointer to the current process. You've got to have something like that.
Yeah,
so you can't do without that. But the problem is you can implement it this way, you can implement it that way. And unfortunately, Linux is implemented it that way. Yes?
Based on your graphing of the exponential growth, can you make a prediction on the range for 2.6 that you would expect?
No.
Before you actually complete the analysis?
I'd
love to see you validate yourself.
Let me put it this way. This work is dangerous enough as it is. My bodyguards are waiting outside. To make predictions of that kind is a bit much. But we'll get to 2.6, don't worry.
Have you found any points where someone has defined a non-kernel module that has actually affected the kernel yet?
Not yet. No, we don't know of any instance of this. We've looking at the Bugzilla type reports. There's nothing of that yet. But now that people know that these things exist, someone presumably is going to go in and do something. Conclusion. Category 5, global variable current, is strangling Linux. That's the only way I can describe it. Work in progress. First, aliasing. The actual figure now is larger than this because some of the aliases are being used as parameters into other functions which propagate the aliasing, maybe closer to 2,000 by now. But certainly there are at least 1,200 instances of definitions and aliases, definitions and uses not of current itself, but aliases of current. So here's an example. We can define TISC as a pointer to a task structure, and we initialize it to current. So when we say TISC arrow exit code is set to code, that's exactly the same as changing that field within current. So as a result of aliasing, there are many more instances we're currently analyzing it. And the second thing is the fine-grained stuff. What we've done up till now, as I said, current's on the left, so that's a definition of current, don't bother me. Now we're saying, aha, not exactly. It's a definition of field state within current, and it's a use of the dereference pointer current. And as I said, this fine-grained analysis shows which fields are most problematic. The interesting result, and this is very preliminary, and I will not be held to it because we discussed this for the first time on Monday, it looks like the effect of the fine-grained analysis is the results for fine-grained analysis are pretty similar to the coarse-grained analysis. Whether you look at the individual fields and do your totaling up, or whether you say to heck with individual fields, I'm just going to look at current, and I'm going to treat current as a single variable, even though I know it's a pointer to a very, very complex data structure, you get roughly the same results, and they're bad. So that is the second work in progress. So now my conclusions. Well, as I think I indicated in reply to your question, unless Linux is restructured with a lot less common coupling and with considerably fewer unsafe definitions, in the future it's going to be unmaintainable. And this seems to be inexorable. So, future work. So what I'd like to do next. I'd like to analyze Windows using our methods and compare Windows with the systems we've already looked at, Linux, FreeBSD, NetBSD, OpenBSD, Mach, and Darwin. Again, what I would do is take 2 graduate students, it have to be at least 2 because everything's got to be duplicated, and let them independently do the same thing we've been doing with all of these to Windows and see what happens. Ladies and gentlemen, that concludes the talk. Are there any questions?
Are there any plans to look at the 2.6 kernel?
Yes, at some future date. Speaking as an academic, it's going to be pretty hard to publish a paper on 2.6 after all of these. It's just a small incremental change. So it would not be of interest, I would imagine, to too many people, and the journals that I publish in are unlikely to accept it. So if someone wants it done and is willing to sponsor it, we'll do it. But it's not a particular pressing interest to us. Yes?
So Linux will become unmaintainable in future?
Yes.
Can you speculate future?
No. We've been looking at this for quite a while. It's very, very hard because there's no other comparable system with which we can say, when this happened in operating system X, it took 2 years. In operating system Y, that took 7. And compare X and Y with Linux and come to a conclusion. Linux is, as far as we can see, unique in this respect. Or not unique. There are other operating systems with lots of global variables, but we just don't have the data on them because the closed source ones we haven't got. Yes?
Do you think your results would be more palatable to the audiences that have had problems with it if instead of saying it becomes unmaintainable, you say it approached the point where re-architecture was required?
Perhaps, but I've never been...
Because it seems unlikely people will abandon it. It seems more likely it will achieve a state where people are going to have to tackle a significant re-architecture.
I would simply say that if I were to mince my words, nothing will be done. At the moment, nothing's being done either. But I think it's important that Linux be fixed. And I think by my giving talks with provocative titles like, is Linux maintainable, which obviously invites the answer no, maybe I can get the attention of people and get things going. And for example, just as a result of publicizing this talk, I received an email this week from someone who's involved with another operating system. Obviously, confidentially, I'm not going to tell you who it was or what operating system, but, and this person has been very worried about the global variables in his or her operating system. and has been wanting to tell the other, let's fix it up, there's too many global variables, and has never had the ammunition with which to do it. And these papers have provided the ammunition for that person. So I'm hoping that now that the work has been published in IEEE Transactions in Software Engineering, which is essentially unassailable. I mean, once it's there, you can't argue the science. You can play politics, you can marginalize me, you can do all that kind of thing. But once it's in IEEE TSE, most people would agree the facts are correct because of the level of refereeing there, peer review and that sort of thing. So now that it's there, I'm going public in the hope that Linux will be fixed. I've got no axe to grind with Linux. I just feel that Linux is very important. Too many people are using it. And therefore, it's got to be fixed as soon as possible. And I believe that not pussyfooting and not putting things nicely would defeat my aim, which is fix Unix. In other words, I am not saying, I repeat, Unix is bad. I'm saying Unix has a problem, let's fix. I think he was first, and then I'll get back to you. Please.
So, has anyone responded to you from the Linux community?
There was a very interesting lot of correspondence on a blog. What happened was I gave a talk, the precursor of this talk, which was entitled 3 Unexpected Results in Open Source Software Engineering. It was on the web. Part of it was Linux, the other two had nothing to do with Linux. It created a lot of outcry. And there were some unpleasant things written, but no one actually approached me directly, which I find very, very interesting. I think one particular site, there must have been, I don't want to exaggerate, but probably hundreds of postings within a period of about 24 hours. And a lot of it nasty. I just ignored. I've had the press coming in, but I've ignored the press totally because until the IEEE TSE article appeared, I did not have credibility. I had an article in IEEE, that's the British proceedings on software. And these papers were floating around. And of course, if you don't like, if you mistrust any of my work, the stuff's on the web, download it and do your own counting. That's not a problem. But it's much better to have some kind of scientific credibility before going public. So yes, I have had responses from indirect responses from individuals, which I've ignored, responses from the press, and I've told them to stop bothering me. So that's the answer. But this talk, of course, is now on the web. Put it up 2 days ago. The papers are now downloadable, so off we go. Please.
I was wondering if there may be some stylistic differences could account for some of this difference. Like, for example, like you showed some code that was assigning this field exit code in current. And so if you just have like current, arrow exit code equals some value, and that can be sprinkled all through your code and count as hundreds of definitions of current. Whereas if you were to have a helper function called, set exit code and have one assignment in that helper function, and then were to call that helper function from hundreds of places, then would your analysis only count that as one definition of current?
Let me say we've looked at this for our aliasing. What we've done is we've taken the separate fields and analyzed them as if they were independent global variables. And we found far too many category files.
Yeah, but the question I just asked, that's not relevant.
No, okay. The question you're asking is the use of functions.
Yeah.
We are aware of some of the problems involved with functions. We have not done the counting of the functions in our current paper, but we are certainly, in the course of our latest work, we are looking at helper functions, if you wish. Okay. There are some of them in Linux already, and we are counting them and adding them towards the total. In other words, that doesn't make the problem go away any more than converting current from a pointer to a macro. No, we would.
Well, I was wondering, like maybe the BSD code base was using these helper functions more pervasively, and so you're sort of undercounting.
It's possible.
Problem there.
It's certainly possible.
What about the module sizes? Are there very similar module sizes in these different operating systems, or is there some systematic difference there?
We haven't looked at the size of the modules. Yes.
Can you talk some about your tooling?
Yes.
The tool that you used?
Very, very good question. We have two tools. One is the Linux cross-referencer LXR, and the other one is our ICE. If you use tools in this work, you can't pick up aliasing. If you use tools in this work, you can't pick up helper functions. The only way to do this is to use something like a cross-referencing tool to find all the instances of your global variables and then look at each one. We then mark them with our code. We have currently, I think, 12 different categories. We find a global variable. Is it a definition? Is it a use? Is it an alias? Is it a comment? Sometimes it will turn in a comment, and we certainly don't want to count those. And is it a call by reference, a call by value? We've got about 12 different categories. And then we have written a Perl script which just goes through this and produces the numbers.
Is that information, both the method and process and the tools, are you publishing that?
Yeah, everything is being published. The methods, we're holding nothing back. We've also written another tool. We've also worked on Java. Of course, Linux is not written in Java, so I didn't report it. But we've looked at coupling in object-oriented languages in general, C++, and Java, come up with a categorization of coupling, and then written a tool to measure coupling in Java programs, and applied it to 10 open-source Java products. And see, the reason we're interested in Java is because to do common coupling in Java, you really got to go out of your way. You've got to define things as public, and you've got to, you've got to overcome all the defaults. Java is busy screaming at you, no global variables, no global variables. So if you want to do one in Java, it's like scratching your left ear. You have to use your right hand to do it in Java. It's very hard. And therefore, we wanted to see how much common coupling there was in Java. And what we looked at, very little. So yes, we have built various tools. And that one's been sent off also for publication. And if you're interested in Java common coupling, you can use it. But the tools we're actually using are LXR, which is mentioned in just about all the papers. The grep script we're now using will be available when we publish the two aliasing papers. And the rest is our eyes, which we have to use. We've discovered that tools just cannot cut it when it comes to this thing. That is why there's so many people involved in this paper. Yes?
Maybe there's 3 unexpected things in
Oh.
the presentation. You have papers supporting 2 of the unexpected things.
Yes.
You haven't published a paper for the 3rd one.
What was the third one? I don't remember my...
The many eyes.
Oh, yes, no. I've got an MS student working on that. We're having real problems on exactly what Linus's law states. And probably in a year's time we'll come up with something.
So I didn't get the context of the question.
Okay, the question is this. I did a presentation last year, a paper called 3 Unexpected Results in Open Source Software Engineering. One of them was the Linux thing, and the 2 others had nothing to do with Linux. That paper I was asked a question about what kind of response have I had. And the reason for the response was that paper was on the web. People downloaded it and said, oh, it's got Linux in it, and started attacking me on the Linux part. The questioner said, he's actually more familiar with the paper than I am. He said, I've actually read it. You've got papers either published or in the press or submitted for 2 of the 3. What about the 3rd one? And the answer is we're still working on that one. The numbers are correct. There's no question of that, but we're having real problems with interpretation, and I don't want to go into into publish until I know exactly what is meant by Linus's law, and I'm not sure I know that yet. Yes?
So I'm curious that, let's take current as an example.
Yes.
In the history of, the Linux kernels patching and, the newer versions being released, haven't you seen like even one anecdotal evidence of a bug fix to current, which indicates that there have been a lot of change in lines of code and things like that correlates your theory?
No, we haven't, because we simply do not have the person power to go through all the bugs. I mean, Linux is, 100 bugs a day coming in? I think I recall that figure. I'm not stating that, I'm just saying that rings a bell. With that kind of thing. The other point is that with Linux, there's no complete set of faults, to the best of my knowledge, available. There's just the latest stuff, earlier stuff. You remember that Bugzilla is 2000 when it first came out, the beta version, but Linux is from 1990. So for the first 10 years of Linux, there is no bug information. What there is, of course, is the email. But quite frankly, I'm not, with due respect, prepared to read through 10 years of email and so on and so forth. The data on Linux is more sparse than on many other similar systems, simply because it was early, and I mean, the strength of Linux is perhaps it was responsible for the birth of the open source movement. I'm not trying to attack Linux, but the point is, because it was responsible for the birth, it was born before all these other useful tools that we can use. Please.
You made slipping out of the technical side of this for a moment. You made a statement that you said that you think that it's important to fix Linux.
Yes.
Given the plethora of both open source and proprietary alternatives to this, why do you feel that is important, given the current exponential curve?
Because for reasons that I don't understand, Linux has been accepted as the standard operating system if you're not in the Windows world. I don't know why people have chosen Linux above any of these, but they have. Maybe it's because Linux has been there so much longer than the others. But for whatever reason, there's a heck of a lot of Linux out there being used for, I think, important work. And people have adopted Linux and are relying on Linux, and that's why I think it needs to be fixed. Certainly, people with the technical competency of the people in this room, if they find an operating system they don't like, they download a new one in an hour's time, and a day later, they're just as familiar with it as with their previous operating system. But for most of the people who are using Linux are certainly not as computer numerate as the people in this room. And they've been trained in Linux, and there's not only that, but they've got all these other programs which work in conjunction with Linux. They've got a word processor which works under Linux and so on and so forth. And for them to change, unlike for the people in this room, would be a major thing. So it seems to me that since we can't change the world, maybe we should change Linux. I mean, let me turn this round. This is, I'm talking at Microsoft. We know there's security problems with the Windows operating system. So why don't we tell people...
Thank you all for coming in today.
And why not tell people to abandon Windows? And the answer is because how many million, if not billion, people are using Windows, and it is incumbent on, I think, Microsoft to do what it is doing, which is to improve the security rather than bail out of the ship.
Well, also going to another operating system is not going to rid you of security problems.
No, that's another thing.
Have you ever thought about looking at products that span multiple OSs? I mean, like Firefox or SendMail or Apache?
Not yet. The problem is one of person power. This is incredibly labor-intensive. I mean, if you just take, let's just take variable current, for example. We've got 12,000 instances of it. Going through that took I don't know how long. And then the aliasing, and then the aliasing of the aliasing, and then all the recursion going through. This is a very big task. So it's simply a question, A, of priorities, and B, as a professor at a publish or perish university, I have to concentrate on things which are going to get me publications, rather than, just as Microsoft is concerned with products which sell rather than products which are interesting, because it's a commercial venture and all that, by the same token, I have to be concerned with things that can be published. So I take your question, but that's my answer. Yes?
Do you use common coupling as a proxy for a measure of maintainability?
Yes.
Saying there's got to be a monotonic relationship.
Yes, precisely.
Have you thought of any other measures? Like you could look at the number of bugs coming in, divide by the size of the database, or...
I've done that in great detail. There's a paper that I've sent off to this to a conference later this year, where I basically, what the paper says is, open source promises to provide all the data we need. Open source does not provide data for maintenance. And the kind of problems are, suppose that, I can just name sort of 10 or 20 off the top of my head, the kind of things which arise. A problem arises in version 10, but it's detected in version 20. This is what normally seems to happen. So in version 20, it's detected and it's fixed in version 23. So your Bugzilla report refers to version 20 because that was when it was first reported, and it refers to version 23 because we fixed it. It does not go back to version 10. If it did go back to version 10, would you believe it? Because we know that faults have got multiple causes. And maybe it wasn't what happened in version 10, but really something happened in version 5. And the other problem is that I think I fixed a bug, and there are a lot of Bugzilla reports that are reopened when we thought we fixed it, but we hadn't. So there's that problem with the data. And then there's the other problem that with the cycles, that version 20 is released. It can only be fixed in version 22 because 21's already out there. It's too late to do anything about it. Then there's the problem of release times. Version 20 is out there for 3 weeks. Version 21 is out there for 9 months. And we've got data on this on things like we've looked at a wide variety of the systems that the gentleman on your left asked me about. Those ones we looked at not Firefox, but we've looked at Mozilla and that kind of stuff. And all the way through, if something's out for 9 months, there's going to be a heck of a lot more false reported than if things are out for only 3 weeks. So you just can take all the data and the other thing is, if you just even look at the data, you get very disheartened. Because if you look at the number of faults reported per week, some of them the curve goes up, believe it or not. Some of it the curve goes down. Some of it there's 2 ups and downs. And then after the next release, you'd expect there's no fault reporting, but there is fault reporting. And we've observed a thing called a double hump, which is about 8 weeks after a particular thing has been replaced by a new version, a little hump appears, and then another little hump appears. I have no idea what this means. So basically the data out there is, unfortunately, essentially useless from the viewpoint of looking at maintainability. And I've written a whole paper simply saying there's data out there, a plethora of it, and it is totally useless from the viewpoint of maintainability. Now, someone who's a lot smarter than I am, I'm sure, will say, you're being an idiot. We can certainly measure maintainability or maintenance effort or whatever you want using some other indirect way other than common coupling. For example, and they will tell us. But I have not been able to find it, and I've never seen anything in the literature. But I'm certainly not trying to say that because I can't find it, no one can find it. I'm arrogant, but not that arrogant. Okay. Further questions?
Where is this posted? Is the link on the...
on this presentation?
Yeah.
Okay, let me go over to the very first page, and let me put this back on projector. There's the link. But I've been told that the audiovisual people will be publishing this very, very soon today.
Okay.
That's what I've been told. I don't know.
Yes. It'll be on ResNet today.
Okay.
Are there any other questions? Let's give the speaker a round of applause.